been going through some of my parts, and I actually found some of the components that's needed. This is some of the electrolytic caps, and we have some of the MLCC caps, the ceramic ones I do have. The picofarad ones I don't have, or I have, but I have to measure them out because it's not the same exact value as here, but I can measure them out and use them anyway. So these 7 picofarads here, I am waiting for the order from Moser to arrive. This 220, 10 microfarad, 10 microfarad MLCC, the 10 microelectrolytic and 1 microelectrolytics, and 220, the 22 nanofarads I do have. And of course I'm going to measure them out before I put them into use. And I've also been looking through what I have of keycaps, and I do have some bags with these. I do have, I think it's 10 in each bag, so it's more than 100, and these are very cheap, probably clicky keys. And I also have about 100 of these keys. They look almost the same, but it's no clicky. And on the board you can see here that they do fit like so, and I do think that they are only going to stick like so, and that the round piece here should not be closed in any way, so it just should fit the hole. But of course when you solder these you need to make sure that they are in the right place, because you have a lot of drift here on each of these. And I'm not sure what I'm going to use. I might use the clicky ones. But for keycaps I do think I am very short. When I have used keycaps in the past, I just bought a cheap keyboard and pulled off the keys. But as you can't do that to every key in this build, I can't rely on that as my only source. And these keycaps are all for the same row, I think. And I have 4 bags, so about 40 keys. And yeah, they're not the same, so I'm not sure how to read out what row this should be. T4004. Yeah, it's the exact same markings on the box. So here I'm really on the wild goose chase. I actually never made a PC keyboard before. I've done some repairs of course, but then it was just replacing things. So you can see here that this is clearly keycaps from another part of the keyboard, as they have a different profile. And I'm not sure how this is going to best fit together, but I will try to see what I can find out about that. When it comes to if it fits on these, yeah, it absolutely does. Yeah, so there are some things we need to find out, but to solder the keyboard all the keys are the same, so I think I'm going to go for these clicky ones. And yeah, maybe just solder them in. And this is a 74LS07, that one I got. And this is a 74LS145, and that one I think I got. I'm not really sure. Other than that, it's just a pin header or two, 1 capacitor, and yeah, you have some 0. The 100 nanofarads decoupling caps, power LED, yeah, and some diodes, one N4148s, these I have. Yeah, I do think I will just solder up this to have it ready when the rest of the components is coming. The print does look a bit so and so, but there are some places for supports here, and this should be nailed to this board in some fashion, and it should be like so. And I might have to sting this up on a steel plate or something to have the sturdiness I need. But first now I'm going to measure up these caps and see if they are within spec. And for that I'm going to rely on my PeakTech. Yeah, I'm measuring this now on 1 kHz. That's probably a too high frequency for electrolytic. I will go for 100 Hz, yeah, and it's 212 for a 220, that's well within specifications. And this should be the same, 207. I don't think it matters on this tester, but I do tend to keep the polarity right where I put the minus to this side when I test electrolytics.
Yes, I was thinking of just doing a short walkthrough of a document that has, taught me much of what I know about electrolytic capacitors back in the day. And this is actually a newer version of a document we used back in school in the 80s. And this is a document from Philips Components dated back in 1996. So it's 10 years after the document that we used in the school when I was taught electronics back in the day. And this is a general walkthrough that everyone that's doing recaps and buying capacitors at least should know something about. And it describes all the formulas and all the terms so that you get them right. And they also teach us some valuable lessons about what drives a capacitor's lifespan and so on. And they first go into some details about how you measure capacitors, how they are constructed, what's the different terms, the dielectric and the electrolyte and so on, and explains what is what. And then they also points to some of the things that you need to do good measurements of capacitors. You have this over here that describes that the capacitance is reduced when you increase the frequency. And you also have this curve about ESR that's dependent on frequency. You have leakage current as it turns to voltage. And you have some other things that's very, very good to put in the back of your mind. And that's failure rate towards rated voltage and the absolute voltage over a capacitor. So that means if you have a capacitor that is rated for a certain voltage, the closer to the rated voltage you are running this capacitor, you have a greater chance of this capacitor actually being destroyed in its lifetime. So that means that you should overrate the voltage on your capacitors. And they also do some descriptions of how this is produced with the can in the insulation and the aluminium foiled, the paper spacing and the rubber sealing and so on. And the rubber sealing should be of special interest to us because the rubber sealing is one of the biggest faults with capacitors. And there actually are two different faults, and these should not be confused with each other. And I see a lot of YouTubers confuse the two main sources of capacitor failure. One that is plaguing, among other things, the Omega 600s and stuff is leakage in the rubber sealing down here. The other fault that I see on a lot of equipment is actually what's caused by a wrong usage of a capacitor, and we are going to go a bit more in depth on that. And this is something I also want you to take notice of. When I was taught electronics, it actually was this figure that was most normal. And that means when you rate a capacitor, you have, it could be minus 10% and plus 30%. And this was the best caps back in the day. They was rated like this. This value I actually never heard of before I saw it here. And this is what is most common on capacitors today. 2020, you actually have a quite wide range of spread of the capacitance on a given capacitor. So if you have 10 of these in your bucket, and they should be 1000 micros, if you have one on 900 and one on 1100, that's quite good and well within specifications. And if you have one that is in this range and it's 950 or it's 1300, it's also well within specification. So this is something you should take note of, that this is not a really exact value to be measuring on a capacitor, and it can be good even though if it has lost 20% of its capacity. It could have been that way since it was new. You have the rated voltage and you have the ripple voltage. The ripple voltage is the amount of fluctuations in the voltage on top of the normal work voltage that a capacitor can handle. And you have to think about this in this way. When the capacitor is charged like this, it goes up to a voltage, and it really does no work if it's kept at that voltage. But if you drain the capacitor so it gets a ripple voltage on top of this, like so, then the capacitor is doing work all the time and it's getting hot. And that is what actually break most modern capacitors and make the top of the caps go boom. It's when you have a high ripple current on a capacitor and the capacitor can't handle the high ripple current, the capacitor gets warm and the top of the capacitor pops. And that's a total different failure from the leakage on the bottom that is caused by a bad seal. And when people talk about the capacitor plage, it's actually both these faults. It's that the capacitor is leaking and it's that they are losing their capacitance and are popping the top off because they are getting overheated because of the added ripple. And that is something that is caused by the frequency curve that you, it's a combination of these curves here. You see that the capacitance is decreasing with increased frequency, and when you are doing on Pentium 4s and other stuff, you are doing step down conversion around the CPU to make the 12 volt go 3.3, 2.8, 1.8 volt. You are actually doing this at a quite high frequency that makes the capacitor lose their capacitance. A normal capacitor is measured by 100 Hertz, but there are high frequency types that's meant to take these high values. And you also have the ripple current capability as a function of the temperature. So as the temperature is increasing and it's quite hot around the modern CPU, the ripple current capability is decreased and it makes the capacitor even hotter. So that's the main cause for failure on motherboards on PCs. And there is also some other things that we can learn from this document, and this is the lifetime of the capacitor and the markings you have to look for. Yeah, here it's described what I talked about on the ripple current, that this will increase an increase of temperature in the capacitor cell. The heat generation depends on frequency and waveform on the alternating current. And this is, as I said, what's causing the temperature in the capacitors to increase and make they go poop. Yeah, and this is also some explanations of what waveforms is handled best and so on. But this is something that many of you are not very aware of. And that is that different capacitors actually have a long or short shelf life. And this is stored under standard asymptotic conditions, and that is about 20 degrees something and normal humidity. And if it's made for 85 degrees, like the most cheap ones, 2 to 3 years storage time, 4 years for 105 degree types, and if you buy the high quality stuff with 125 degrees, then it's 10 years. And this is within Philips specification, and that means that you could have components that survive this with a quite degree of confidence, but here is what Philips is using, and then use a confidence level of 60%. So they are about 60% sure that this result will be given. And that's not much better than flipping a coin. And you also can see here the useful life if you have the capacitor in a high temperature environment. And if you have a normal capacitor, it will do 2000 hours at 85 degrees, 4000 hours at 75, and 8000 hours of 65. So that's quite a huge drop. And this capacitor will last 20 years with 40 degrees Celsius, and this is the long life types. And if you have the 120 degree types, they will live more than 50 years at 40 degrees. And that is quite an exceptional long lifespan for a capacitor. Because if you have this stored and you say that you are not using this equipment all the time, 50 years, the capacitor is not dead yet. And if it's been stored good and cold, this could be made to last more than 50 years. And they also have some other graphs to show about the same, and that is the lifetime expectancy that you can have with lowering the ripple current and the ripple voltage on a capacitor in a high temperature environment. So both these values, the actual ripple current and the rated ripple current. If you have a capacitor that's rated for a higher ripple current, it will also last longer. And this is the same with 105 types capacitor. You actually could have quite the high lifetime by lowering the temperature and lowering the ripple current. 200 times the actual rated capacitor life you can get out of this. So this is very useful information when you are buying new capacitors for stuff. Don't copy the old boom one-to-one. Buy better caps where they actually are suited to be used. So you can see here the difference. You have 3 times the lifespan on a 105 degree type as a 85 degree types with the same use pattern. And also, if you change your caps, you do have to remember this curve. This is the failure before you have taken this into use, and this is the X factor. This is the risk you are taking with taking a good known system and replacing a cap. You can replace it with a cap that is in with this specification, and you can take a cap that is about here and replace it with a new one that is in this band. And that means you make the system faulty, and that's one of the reasons why I don't recommend to change capacitors before they are prone to fail or if they actually measure bad. Because you take the risk if you are changing 20 caps at once in a system and you have 2 that is in this condition that fails before they are new or when they are quite new. You will actually have shortened the lifespan of the systems quite a lot. But of course, if you change the caps that is in this part of their life cycle and even up here, they are still doing okay, but they will fail eventually, then it's of course a good reason to change them. But caps that are in this area of life, you should not go about changing them because you increase the risk of destroying the system and it won't do anything good. It won't make the system last longer. So this was some of the knowledge that you can take from one of these old datasheets from Philips. Philips don't make electrolytic caps anymore. Actually, I don't think they do. I've not seen them manufactured for quite some years. They typically was these blue tubes, and they had quite the high quality and reputations among their peers when they was in production. And other manufacturers of capacitors use the same technology, so they are about the same. Some of course have better production quality than others, but that is because of internal quality control and higher quality components. Yeah, the plan now is to gather the components needed for the keyboard PCB and just solder this up so that it will be ready when I get the rest of my components. And I do have everything I need for populating this board and making it totally finished. I do lack one 7407 chip, but I do have a solution for that. So let's just gather the rest of the components and start soldering in, and we see what problems we got underway. On this board it's only a handful of components. That's not the case for the keyboard, and that is these 1N4148 diodes, where I don't remember if the yellow ring that's around these pretty old diodes, if this is the cathode, and as we can see it is. Yeah, and since we have very few components here, I'm just going to place them into the boards and make them finished for soldering by bending the legs outwards for every component, and then I do some soldering when I have placed these components. Yeah, I have not looked very throughout on the schematics for this keyboard, but that we have 3 470 ohm resistors make me think that this is the resistors, that's the series resistor for the 3 LEDs that's on this board. It's quite a typical value for dropping down 5 volt and yeah, be left with acceptable current through a LED. Yeah, and there only are these 2 sockets on the board. It's one 14-pin and one 16-pin socket. And you also have only 3 caps. It's 2 ceramic 100 nanos and 1 electrolytic caps, just a small one. So now it's time for the keyboard case, and I don't think this will be an easy task because these don't fit really well in the holes. You have a good way of slack here and you have quite some adjusting to do, and if I'm going to do that like this on every key, this is going to be quite time consuming. Now I'm going to try to fix up some other keys and we can see if we can find the easiest way to solder in these keys afterwards. But first we have to make in some samples so we see how this goes. As I am quite unfamiliar with soldering in keyboard keys, I do wonder if original keys would have been easier and if these additional holes that are on the sides of the soldering pads, if they will be filled with some plastic that should make the adjustment easier. Yeah, as you can see, the first row of just 6 keys was quite time consuming, and on this row I'm trying a different approach. I take and solder in the key on the leftmost side and the rightmost side, and I try to span a steel ruler or something over here and have the keys go, as a pointing key when I try to place the other keys, but I'm not sure how this goes because both the plastic hole and the holes for the each leg of the 2 legs that's actually in these switches are too small for the holes on the PCB, so there is a lot of wiggle room. And even though it's better to have some support in the ruler than not having any support at all, I still have to do some adjustment for each key, and I do think that's likely because the light weight of the keys is not enough to keep it against anything. Was that easier? I'm not so sure. It was the first full row that I've soldered and this took a lot of time and it was a lot of adjusting afterwards, but at least you did have a straight edge to adjust things against, even though it was not easy to get the small pieces of plastic to adjust against the steel. And here we test that the keycaps actually are, that there is space enough to put ordinary keycaps on this keyboard, and that it seems like it is. So I'm going to continue forward full speed ahead on this keyboard to get all the keys soldered in. And again, it's lots and lots of adjusting on the 2 outermost keys to get the steel ruler back in place to use as ruler to put all the other keys against when we try to place them. But this is not a very speedy way of making keyboards, that's for sure. Yeah, here I first try to make a speedier approach where I place more keys inside the steel ruler and try to solder them in, but then I was thinking maybe it's just as fast to put 1 and 1 key and let go of the attempt to make more than 1 key stick at a time, because then you get 1 and 1 key properly adjusted. And I do that for the next couple of keys. Is it faster? I really don't know. I do think it slows me down a bit. And here I try yet another attempt to use the ruler. I put it a bit on the side so the support goes further up on the keys. And I was thinking that this will give me a better edge to have the support on. But then again, I'm not sure that if it helps, because the light weight of these keys make it very difficult to make them even against anything. And here I skip the caps lock key, as there should be a LED underneath it. And for the next line, I again try a different approach. I put the ruler the other way and let the keys rest against the face of the ruler. And this might seem like a better idea, but then again the keys are so light that they fell all over the place. The biggest difference was that even though some of the keys were more straight in the way of turning in the socket, there also was some of the keys that was not totally flush with the PCB, because they tended to fall out on the downside of the casing, because the solder pins are on one side of the keycaps only. As you can see in the photo that I have embedded in the video here, you can see that almost 80% of the key has no support at all against the PCB. And I discovered that I have been a bit too eager on these keys. The code key should also have a LED beneath it. I did notice it earlier, but I just forgot it in the heat of the fight against getting these keys straightened out. So I do have to desolder this, and I do have to find some 3mm diodes to put underneath that key and the keycaps key. And one of them should be yellow, the other one should be red. So I think it's quite easy to find, and I do think it's ordinary 3mm LEDs that should go there. And as the diodes are in blank plastic, I have to test, and this is the red one, and it should go under the caps lock key. And as we can see, it fits rather nice in the space that's reserved for a light on these keys, and they are transparent, so I think this is just going to shine through just fine. When I'm testing these LEDs, I put on a 10 milliamp current limiter on the power supply, and I turn it up to about 2 volt. That will not destroy anything. As you can see, this is the yellow LED, and you use the long lead for the anode and the short lead for the cathode. And here I'm not satisfied with the markings on the board. I am not sure which way the diode should stand underneath the keys. The power LED is marked with where the cathode should go, but the LEDs underneath the keys are not. So I will measure out what goes from which part, what's to the ground side and what's to the power side. And what I know is that these resistors up on this PCB is connected to the anode side of the LED. So I'm just going to measure out where you have about 470 ohms to which leg on the PCB, and that's the way we are going to put the LEDs. Now things are starting to look almost finished, but we still have to place the keys over where we have placed the diodes. And now it's important to see that these keys are coming flush with the PCB and they are not higher than the other keys. But we have tried the diode, so I think that should go just fine. In the description there should be a 16 pin 2x8 90-degree angled pin header. I don't have that. I have a 20 pin header, but I'm just going to clip away the 4 unnecessary pins, and I'm just going to solder this in. It will fit just fine and meet the purpose of what's intended to go from this keyboard. To help me when I solder this in, I use a cardboard strip that lifts the socket from the PCB to make it easier to put the actual connector onto this afterwards. Yeah, so now we have only one component left. It's the RN1 network, and that's a 4.7K bust resistor network with 5 resistors. And that is a bit of a tricky one because I only have this with 8 resistors or 9 pins, so I'm just going to cut it. What? You are thinking this crazy Norwegian is at it again. What is he thinking now? But this is really simple because this is only a passive component. So what we are actually doing here, we are not cutting the black package of the resistor network, we are only cutting the legs that we don't need, and that is the 3 resistors that is furthest away from pin 1 on this network. And we just cut them flush with the plastic, and they won't touch anything on the PCB when this is soldered in. So that's it. We have soldered the keyboard and finished everything here, except that we have not put in the ICs yet. And I do have the 145 that should go into this socket, but the LS07 that should go here, that's just a buffer. I either have to make my own as I have done before, or I have to wait for that to ship, because I only had one and that was already taken for the main PCB of the Omega that also needs one of those. But even though it was a nightmare to solder in all these switches, I think the result was okay. There still are some crooked teeth in here, but it's very difficult to make the adjustment to make them totally straight.
So, thanks for watching. Hope to see you again in my next installment in this series. This was the second installment, and I'm going to need at least one more with soldering and components before we can actually try out this project with power on. So, thanks for watching. Hope you liked the content, and please hit like and subscribe if you want to be notified when we post new videos. Hope to see you in the next one.